Welcome everybody to today's special year seminar on theoretical machine learning at the Institute for Advanced Study. Today we are delighted to have Professor Arthur Gretton as our speaker. Arthur is a professor at University College London and is known for his extensive contributions to kernel methods, non-parametric hypothesis testing, and general models. He's best known as the co-inventor of maximum mean discrepancy, a dismetric on probability measures that employs kernelization to achieve asymptotic consistency and high power when used as a two-sample test. He has served as an associate editor of the IEEE Transactions on Pattern Analysis and Machine Intelligence, an action editor for the Journal of Machine Learning Research, a member of the Royal Statistical Society Research Section Committee, a program chair for AI Stats, and a member of the program committees for NeurIPS, ICML, and COLT. Today, Arthur will tell us about critic functions and implicit general models. Please welcome Arthur Gretton.
Okay. So thank you very much for the invitation. Right, so I'll be talking about the critic function of implicit generative models. So broadly speaking, the goal that I have in this talk is to train a generative model. So let's say that I have a set of samples X from a distribution P. I don't have the distribution in closed form, but I just have samples from it. So in this slide illustration, I have a set of pictures of a bedroom. And I wish to create a generative model which is going to draw samples which will match this target distribution. So I have some neural network mechanism, and I want to train it so that it creates samples which have the same distribution as far as possible as my target. So to accomplish this task, what I need is a critic function. So my critic function is going to be something that compares my source distribution P, my real bedrooms in this case, to my generated distribution Q, so my artificially generated distributions. And this critic function is going to give an indication to my generative neural network that these distributions are getting closer. So it will be, in some sense, the loss function for my generative model. So these critic functions are going to be the focus of my talk. But we're going to see at some point in the talk also that the critic functions can actually enter into the generative model and help it out. So that's something that I'll be covering. All right. So to give the outline and the contents, I will start with a description of P divergences and critic functions that we derive for them. So P divergences are one, set of divergences between probabilities, and they will give rise to a set of useful critics for training generative models. I'll then introduce a different class of models, which are the generalized energy-based models. So these, as you might guess from the reference below the headline, are a new topic of research on my part. And I'll also warn you that this is the first time that I'm actually presenting them. So the slides might be a little less polished than usual. So please feel free to ask me if there are questions. Then I will transfer to a different class of critic functions, which are the integral probability metrics, which are a different category of critic functions to the Phi divergences. Finally, if I get a bit of time, I'll go into a more speculative mode, and I'll talk about the role of gradient regularization for critic functions. So in this case, I don't have theory, notwithstanding that this is a theory seminar. So that's more of a sort of call to arms to try and figure out the theory that corresponds to some interesting empirical behavior that we've seen. So I may or may not get to that part, but if I do, we can discuss it a little. Okay, so that's the topics for today. All right, so let's start with divergence measures. So broadly speaking, there are two categories of divergence measures that I'll consider based on two different concepts. The first concept is the difference in probability measures. So broadly speaking, if I have a difference of P and Q, P minus Q, and if this difference is 0, then P and Q will be the same. The second category of divergences that I'll consider is, in some sense, a ratio of P to Q. So if this ratio, however I defined it, is 1, then P and Q are the same. So these are two different philosophies, if you like, of comparing distributions. Now, on the left-hand side, this difference in distributions gives rise to the integral probability metrics. So here I want to witness the difference in distributions. So I look for a function, g, in some category of functions, calligraphic h, that maximizes the difference in expectations under p and q. So h is going to be well behaved in some sense to be specified, and the functions in this h witness the difference in p and q. So if p is equal to q, then whatever function I choose to witness the difference, this difference will be 0. So these are the integral probability metrics. Then on the right-hand side, well, how do I witness the ratio of p to q? So I'm going to assume that p and q both have densities with respect to the leg, and I'll also assume that the ratio of p to q is well defined here. Then I'm going to compute the expectation of a function of this ratio, the ratio of p to q. This function phi is going to have a few useful properties. So firstly, it's going to be obviously 0 when the ratio of p to q is 1, because when the ratio of p to q is 1, then p and q are the same. It's also going to be convex for reasons that are going to be useful to us shortly, and it's lower semi-continuous. So let's begin by spending a bit of time on the right-hand side of this world of divergences. So we have a number of divergences in that category. Hellinger is one, KL is another, chi-squared is yet another. So there are many divergences that we know and love on this side of the slide. Okay, so let's just recall from the previous slide the definition of the phi divergences, where we've got this expectation of phi of the ratio of p to q. I will focus here specifically on the KL divergence. So here phi of its argument is just u times log u, where u is the argument. And then with a little bit of manipulation, I get the KL divergence. So the expectation under p of the log of the ratio of p to q. And this is the divergence measure that I'm going to be considering here. So are phi divergences good critics? Arguably not, right? So remember, the critic function is something that I'm going to be using to compare samples from P and samples from Q. And ideally, what it's going to do is it's going to give a useful signal to my generator, which is generating Q, that tells me that I'm getting Q closer to P. Now, if I'm generating samples in some very high dimensional space, for instance, images, it's almost certainly the case that the support of P and Q is disjoint. So Léon Bautour and his co-authors made very strong arguments in that direction. When the P and Q's support is disjoint, then the ratio of the densities isn't well defined. And so we've got this awkward situation where, in this case, the KL is infinite, the Jensen-Shannon, which is another phi divergence, is log 2. And these divergence measures don't change at all as I move my support of P around, as long as it's, as I move my support of Q around, I should say, as long as the support of Q and P is disjoint. So think of this, I've shown it in cartoon form in the corner here, as an angry lecturer, and the lecturer always yells at you that you're wrong, whatever you do, because it's not allowing you to notice that your probability mass of Q is approaching P, as long as the support is disjoint. So this is a little bit surprising, because in the great majority of the GAN literature, it's claimed that the critic function is based on a phi divergence. So something's going on. So clearly we're getting something practical derived from a phi divergence, which is more helpful in training a generative model. So what people might be using in practice is derived from a phi divergence, but has slightly friendlier properties. In particular, what we're going to be doing is getting a lower bound on the phi divergence, and this is what we'll end up optimizing. So you might argue that minimizing a lower bound is not a good idea, but in this case, it's a lower bound on something that, as we've seen, is always infinity. So in fact, the lower bound will be a practical signal, even when the KL is not. So let's see how we might derive this lower bound. So here is our KL. Well, here is in fact a general phi divergence, so I'm not going to be specific to KL just yet. And what I'm going to do is I'm going to replace the phi function with a variational form, which is expressed in terms of the dual of phi. So recall that the dual of a phi function, dual of a convex function, is a slope-intercept form of that function. So phi star takes the slope of the function and returns the negative intercept of the tangent line where it hits at that slope. Okay, and we can express phi in terms of this dual form as I've written here. So I've got the expectation under Q of sup of fz. So fz is a scalar which is changing according to z. Of this expression here, P on Q fz minus phi star, the dual at fz. This is an equality. So as long as fz is able to change according to z, so it always matches this ratio P to Q, then this is exactly equal to phi. But now let's say that I use, rather than an arbitrary fz, a restricted class fz. So a smoother class, for example. Then this is going to be a lower bound on my phi divergence. So if this calligraphic h is a smooth function class, then I'm going to end up getting a lower bound on my initial phi divergence, which is expectation under p of the smooth f at x minus expectation under q of the dual function of f at y. This bound is going to be tight at a function of diamond, which is equal to the subgradient of phi evaluated at the ratio of p to q. So if phi is differentiable, this is just the gradient of phi evaluated at the ratio of p to q, as long as that ratio is defined. All right, so this is the lower bound on the phi divergence that we're going to be using. Let's look what happens when we use the KL. Okay, so here is my KL divergence, the log ratio of p to q, expectation over p. Now let's find this lower bound in terms of the dual of phi. I'm going to do a small reparameterization here, which is why there's a little bit of a difference in the form of the equation with respect to previous slide, but this is some very minor algebra, but it'll make future slides more clear, so that's why I'm doing it. So I've got this lower bound in terms of sup over f in a calligraphic h, a smooth class of functions, of the negative expectation of f plus 1 minus expectation under q of e to the minus f. So this e to the minus f derives from my dual function of phi. So remember, phi for KL is u log u. So this is now a variational lower bound on KL in terms of f, which belongs to a smooth function class. Now this bound becomes tight at f diamond, where f diamond is the negative log ratio of p to q. So for instance, if I've got p and q, which are Gaussians with different means, the log ratio is just a straight line, and f diamond is this straight line here. Now, let's say that we want to compute this in terms of samples. Well, we can do that, right? So here I'm replacing my population expectation over f with the sample expectation over f. And I'm doing the same with the exponential of the negative f on the samples from Q. Okay, so now this is an empirical expression. And if I have a nice smooth class of functions, I'll be able to get an approximate lower bound to my KL, which I'm computing from these smooth functions. Okay, so this in sum is a KL approximate lower bound estimator, which we're going to call the KL divergence. So one should be very careful not to confuse the KL divergence with the KL divergence. And it's actually this variational lower bound, which is what people are actually using in GANs. So let's see if our KL, our variational lower bound, is better behaved than our KL, our original phi divergence. Okay, let's look at some of the topological properties of KL. We're going to make a few assumptions, both on the function class and on the domain. So we're going to assume a compact domain, and we're going to assume that we're using a smooth function class that is nonetheless dense in the space of continuous functions with respect to the infinity norm on this domain. We're also going to assume, and this is needed in the proof of the theorem below, that if f is in the function class, then negative f is in the function class. And if I scale f by a constant, which is greater than 0, then this is also in the function class up to some maximum. If all of these properties are true, then I have a very nice behavior for my KL, which is that it's non-negative and 0 only when p and q are the same. So that's good because that tells me, at least in some respect, that my critic function is helpful, that it's going to only be 0 when p and q agree. So are the requirements that we are placing on our calligraphic H too strong? Well, there's been quite a few studies on the richness of neural net function classes. So for instance, our calligraphic H might be dense in the space of continuous functions on compact domains when H is in the span of ReLU type functions, or ReLUs raised to some integer power. So at least this is a class of neural network functions which would satisfy this denseness requirement. So this tells me that my KL is 0 when p and q agree, but it's still missing something. It's not telling me if KL is going to be a helpful critic to me or not. Because remember that the difficulty with the original phi divergences were that they didn't tell me that my mass of Q was approaching the mass of P when these masses were disjoint. So it turns out that KL has actually, the variational lower bound does have a much nicer property than a phi divergence, which is on this slide. We're going to make the additional assumption that the functions in calligraphic H are Lipschitz with constant L. If this holds, then our variational lower bound, our KL, approaches 0 if and only if our Q weakly converges to P. Okay, so this is a very nice property. If I have weak convergence, then my KL is going to drop to 0. So this is a property that the phi divergences don't have. Just as a sketch where this idea can come from, if we start with our KL, which is written here, just the first line of these equations is just to remind you of the definition. We can do some very simple manipulation to rewrite that as a difference in expectation under Q of f minus expectation under P of f minus a term here, which is an integral of a function which is non-negative. And therefore, we can upper bound the KL by the difference in expectations under Q and P of f, which is in turn upper bounded by Wasserstein 1 times some constant. And so this is nice because if Wasserstein 1 goes to 0, which it does under weak convergence, then that forces KL to go to 0. And we also have the opposite direction, which follows from a result in this paper by Yu, Busquet, and Chaudhry. So Sanjeev will be very familiar with these notions of divergence. I think in his paper, he calls them the neural network distances. So these distances are much better behaved, indeed, than the original phi divergences are. All right. So this is nice. Let's look at a couple of examples. So in this case, I'm going to be computing my KL using a particular class of smooth functions, which are the reproducing kernel Hilbert spaces. And we're also going to penalize the RKHS norms. So the reproducing kernel Hilbert space norms of our functions. So recall that the RKHS norm is a measure of smoothness. So if we're penalizing it, that ensures that we get a smooth function. So we'll call this one the KL smoothie. And what we'll notice is that if we're using the KL smoothie, that even though the probability mass is disjoint, first of all, our function is finite. But second, as the mass of Q approaches as the support of Q approaches the support of P, what you see is that this is decreasing. So the KL smoothie, our variational lower bound on KL, is behaving well. Okay, and it's indicating to my generator that its mass is approaching the mass of P. So I'm going to indicate this using a friendly professor who is helpful, who is giving useful feedback to the generator, and is telling the generator that they're getting closer to the target when this is occurring. So it would appear from this that our KL is, definitely and unambiguously a better divergence measure. But KL also has some, I guess, disadvantages. So to indicate a disadvantage of KL, I'm going to use the example on this slide. Yes?
Was there?
Was there a question?
I guess not.
Okay. So yeah, please ask me. I mean, I'm very happy to take questions. I'm not sure what the protocol is, but if anything's unclear, please ask me and I'll do my best to answer. Okay, so I'm going to indicate on the slide where the KL, the variational lower bound, can mislead you. So this is a very simple example. P and Q are two Gaussians with the same mean but different variance. And along the x-axis, the variance of my Q, which is to say my generated sample, is becoming much, much too narrow. Okay, so this is in the GAN literature what people call mode collapse. So the GAN is creating samples on a much smaller support than the target distribution. And as the mode collapses, so as the red sample gets narrower and narrower, the KL is getting bigger and bigger, as indeed it should do. However, my variational lower bound isn't able to track the KL. And the reason is because we've ensured that the log ratio of P to Q is a smooth function. However, when the variance of Q collapses with respect to P, this ratio is not a smooth function. So our KL is actually severely lower bounding our KL. And it's not sufficiently penalizing us for having this mode collapse. So this is, in a way, an indication of why a critic, based on this variational lower bound, isn't very good at preventing mode collapse, because basically it's not penalizing mode collapse as severely as it should do. So this is a disadvantage of this variational lower bound. All right. So this is a discussion of the critic functions that people are using when training implicit models. I'm now going to introduce a new class of models, which is a little different to GANs, which are generalized energy-based models. So as I said at the start, this is very new, and this is the first time I'm speaking about this in public. So please interrupt me if anything isn't clear, and forgive any misadventures on the slides. So just to remind everyone how a GAN works, normally with a GAN, you have a generator, which I've shown here as a little student who's learning to paint, who generates a set of objects, in this case, dogs. The teacher, the critic, which we've talked about quite extensively, compares the set of fake dogs to the set of real dogs and gives feedback to the student. And this iterates until an equilibrium is reached. So the student stops improving, or the teacher is no longer able to tell real dogs from fake. Okay, so this is what happens when we're usually training a GAN. What happens after we finish training the GAN? Well, what we do is we take the critic and we throw it in the trash, and we keep the student. But this seems, I think, unfortunate. Like, it's not obvious why we are doing this, because the critic, unless the critic function is perfectly flat, so if you recall the phi divergence critic, if this phi divergence function isn't perfectly flat, then the critic still contains information about the mismatch between the real and the fake dogs. Okay, so the student is still not creating samples that match the target distribution, and the critic knows that, but we're throwing the critic away. And this seems like a mistake, like we've got information that we're not using. So how could we modify this generative model to incorporate critic information? So just as a reminder of what the generator is doing, this is a classic instance of a generator here. it takes noise distribution on the left-hand side from some known distribution, say Gaussian, and it pushes this noise distribution through a bunch of filters and outputs samples in a much higher dimensional space. So loosely speaking, not being mathematically precise, one could sort of say that you're covering a submanifold in this higher dimensional space based on the samples drawn from a much lower dimensional space. Okay, so this is what our critic is doing. So how do we sorry, that's what our generator is doing, I should say. So how do we take our generator and incorporate, in some sense, critic information into it? So to do this, we're going to define a class of models called the generalized energy-based models. I'm going to express this on the top of the slide as Q, B theta, and E. B theta is my generator, and E is my energy function that derives from my critic. So to show in equations what I showed graphically in the previous slide, my generator with parameters theta is going to take a Z drawn from an eta, a distribution, and then push it through a B theta. So this is my set of neural network filters to produce an X in a higher dimensional space. So Z is low dimensional, drawn from a known distribution, X is high dimensional. And these are, for example, the images. All right. But what we're going to do, which is different to what a GAN does, is then to reweight these samples according to some importance weights. Okay. So my F, which is going to depend on both Q, which is my generator distribution, and my E, my energy function, is going to be given by this exponential here. So an energy-based model where the log partition function is integrated over my Q coming from my generator. And I'm going to call calligraphic E here the energy function class. And capital E is going to be a particular instance of a function in this energy class. So F QE is the Radon-Nikodym derivative of my model, QBE, with respect to Q, my generator. Now, if Q has density with respect to the Lebesgue, then this is just a standard energy-based model. But as we've seen, what's going to be very interesting is that if Q is on a much lower dimensional submanifold, so it doesn't have a density with respect to Lebesgue on the image space, but I can still define an energy-based model, even in this case. Sorry, a general energy-based model, even in this case. So how do I fit a generalized energy-based models? I'm going to fit that using a generalization of the log likelihood. So I'm just going to say, well, I'm going to integrate my log of F from the previous slide with respect to P, where P is the distribution over my samples. Okay, which is going to be expressed here as the negative of E dP minus log of the log partition function integrated over Q, integrated over my generator. So in the event that my KL between Q and P is well defined, so if I was in this naive situation where P and Q both had densities with respect to the Lebesgue, and P was absolutely continuous with respect to Q, and my KL was well defined, then the above would be the Donska-Varidan lower bound on the KL of P to Q. Okay, so expectation with respect to P of my exponential, my energy-based model, divided by Q. And this would be tight if the energy function was the negative of the log of the ratio of P to Q. However, in my setting, Q is not going to have a density with respect to Lebesgue. P and Q might be mutually disjoint, so they might share no support. They might be mutually singular, and yet I could still consider this generalized notion of log likelihood and use that to fit my model. So this idea of incorporating an energy function into a GAN, where the energy, as we're going to see, is going to be in some sense derived from the critic, appeared twice simultaneously this year. So both in our paper and in another paper by Che, Zhang, and co-authors in Mila. So we've also put the code online for this. All right. So we've got this notion of generalized log likelihood, which we're going to then try and use to fit an energy-based model. So there are three things we need to do. First of all, we need to fit our energy, right? We've got this loss function, but we need to fit the E from it. Second, we need to fit our Q, our generator, our base measure. We need to find a way to optimize over that. And finally, having fit our E and having fit our Q, we need to sample from this thing. Okay, so these are the tasks we have. Before I go to those tasks, I'm just going to show you graphically what this model is doing and why we might want to fit it. So let's say that our target distribution is supported on a 2D plane, but it's a one-dimensional submanifold. So this is what I've shown in this plot here. So this blue wiggly line here is the support of our distribution in 2D. But as you can see, the support is a 1D submanifold in this 2D space. And this is a sort of realistic situation when you're trying to generate images in high dimensions. Now, the mass on that support is shown by this line here. And so you can see, some parts of the support have more mass, some parts have less mass, and this is going to tell me how many samples I've got on different parts of this support. Now, let's say that our generator Q has been trained in such a way that it's actually got the support correct, but it's placing the wrong mass on that support. So this is what I've shown in red here. Okay, so it need not be the case that the red support and the blue support match, but for the purposes of this little drawing, I'm going to assume that my generator got the support right. However, it got the mass wrong. So it's putting too much mass in some parts and too little mass in other parts. Now, this green curve here is what happens when I fit a generalized energy-based model. So what it's done is it's taken the mass which has been placed by my generator, my Q, and then it's reweighted it to give a new Q, which is a function not only of my old generator, but also of my energy function. And this green function is closer to my blue, so it's a better match for the target. Okay, and so this is, in a sense, a difference over a GAN, where the GAN would only have the red function, but it wouldn't be using the additional information which my energy function is giving me. All right, so let's go through our tasks. So our first task is to learn the energy function. And I'm going to learn the energy function by fitting this generalized notion of likelihood here, okay? And I'm going to fit this FQE, which when I take the log is going to give me the negative of E integrated over P, my real samples, minus the log partition function with respect to Q, which is my generator support. Now, this is a little bit awkward to fit because of this log partition function. This is always a very antisocial quantity. So we're going to need to do something about that. Okay, so what we're going to do is we're going to exploit the concavity of the logarithm. So the negative log is always greater than or equal to minus C minus e to the minus C times Z, where Z is the argument of the log. So this is just using the tangent of the logarithm at Z. QE, which is the log partition function. And obviously, this lower bound becomes tight when C is equal to log of Z. So let's replace that lower bound. And what we get then is the following function to optimize, okay? Which is the negative expectation of minus E minus the negative exponential of minus E plus C plus 1. So this lower bound is actually the quantity that we're going to try and maximize here. And looking at this expression here, you should hopefully be getting flashbacks to some of the earlier slides, because when we derived our KL, our variational lower bound on the KL, then this was a very similar form to here, without the C quantity. but we had negative of some function dp, negative minus exponential of some function dq plus 1. Okay, so this is very similar to and reminiscent of the critic function in a GAN. It's not quite the same thing, however, and one should be cautious of this because we also have had to estimate as part of our model the log partition function, the C function here. When we maximize jointly over E and C, then we're going to get our maximum likelihood estimate of the energy, E star, and the log partition function, C star. And at the optimum, if P and Q actually did have densities with respect to the VEG, and if the ratio of P to Q is well defined, then this C star would just be the negative log of the ratio of P to Q. But of course, here, Q and P might be disjoint, the ratio might not be defined, and so we have to be a little bit more cautious here. Okay, so we have now a nice function we can use to optimize our energy, but we also need to learn our generator. And remember that our generator is given by this implicit model, right? So I've got X, which is generated according to, I generate a Z from an ether. I push it through my neural net, which is parameterized by theta, and this gives me my samples. And I now want to find a way to optimize over the parameters theta of this generator function. So to make my notation concise, I'm going to define calligraphic K of theta as the F from the previous slide. So this lower bound on my generalized log likelihood, as a function of theta. So as a function of the parameters of B that I'm trying to learn. Now, fortunately, we are able to compute the gradient with respect to theta of this K. So this is a theorem that we have in our paper. So this K is Lipschitz, it's differentiable for almost all theta. And it takes this expression here in terms of E star, which is the maximum of the calligraphic F from the previous slide. So we do need to get the optimum of the E from the previous slide to get an unbiased estimate of the gradient. If we haven't reached the optimum E, then we're going to get a biased estimate of the gradient. Okay, but here is our gradient in the event that we learned our E, which achieves the supremum from the previous slide. So this is good because then we can use our favorite optimizers, our stochastic gradient descent solvers or Adam or whatever to optimize over the generator parameters as well. Obviously, this gradient is going to require us to make assumptions. So this requires assumptions both on the energy function class calligraphic E and on the class of generators that are using B theta. In particular, the class of E functions has to be both L Lipschitz and L smooth with respect to X, which is the argument of the energy functions, and also its parameters, C. Okay, and for the B theta, which is our generator, that has to be also Lipschitz and smooth with respect to both the Z and theta, and the smoothness with respect to theta, its parameters, is in a sense that it's going to depend on Z. So I'm not going to put the expressions here, but just be aware that one has to be a little bit careful about the conditions on both the energy class and the generator class for this gradient to be computable. Okay, so we've learned our energy, we've learned our generator, our base measure, and now the question is, how do we sample from this model? Okay, so let's say that we've trained our model and now we want to draw samples from it. So recall the notation we use for our end-to-end model, which is Q as a function of both B theta, the generator, the base measure, and E, the energy function. And recall that we get our base measure by passing noise through B theta, and then our energy function is this energy-based model here, e to the minus E on Z. So if we were wanting to get expectations over a test function, so some function in the space X with respect to this model QBE, this is how we would do it, right? We would draw Z from eta, we would pass the Z through our V, we'd compute G on that, and we'd importance weight it by FBE. So that tells us what the form of the posterior over Z is. It's the eta, which is the noise that passes in our network, multiplied by F, evaluated at B on the Z. So to sample from this posterior, you just use your favorite Langevin diffusion derived algorithm, Mala, Euler, HMC, which exploits the gradient of the model. And this is going to give you samples in the latent space of the generator according to the posterior of our end-to-end model. So these are going to be samples in the latent space that will incorporate the information from E, which is our energy function. And then to generate from our model, we just take those samples from the posterior, we pass them through B, and that gives us our samples. So let's have a look at what this looks like. So what we've shown here, using actually both our generator here and our critic are relatively simple networks. So we're not using some incredibly complicated networks here, and we're doing this on CFAR. But we're just running our Langevin Monte Carlo from some starting point until it reaches a stationary distribution. And what you can see on each row of this figure are the samples that we get out. And you can see that they go from being sort of blurry and ill-formed to something reasonably recognizable. So these are the samples that we get by drawing from the posterior over our latent space and then pushing those on the generator and then pushing those latent samples through the generator. So what we found empirically is that all else being equal, you always end up getting better samples if you incorporate the critic, if you incorporate the energy. So think back to the GAN. What we did with the GAN is we trained the GAN until convergence, and then we threw away the critic. What we're doing with the generalized energy-based model is we're doing something very analogous to a GAN, where we have our critic, which is the energy function, and our generator, but we're not throwing away our critic. We're keeping our critic, and we're using that to improve the sampling by using parts of the latent space that give better samples when you push it through the generator. So I think this is maybe a good time to pause and see if there are questions about this bit before I go on.
Okay, are there any questions? Okay, so I have one. Oh,
sure.
Go ahead. Someone.
No, you're going to read them, right? As usual.
Yeah, but you can go ahead as verbal.
Okay. So this framework, I mean, still uses distributions represented by not so large nets, right? Deep nets.
Right. So exactly. So the by not so large nets, you mean B?
Realistic.
Right. No, absolutely. Yeah. Yeah. Mm-hmm.
So I mean, like some of the assumptions probably are not satisfied, like the smoothness. So.
Right. So what you're saying is let's see. So the differentiability. Do you mean?
Well, even if it's differentiable, but then to say it's smooth for some reasonable smoothness is probably not going to happen, and so on. I mean, you're trying to. I mean, you're taking a calculation that's sort of, you know, in the space of all functions is exact, but then when you approximate functions by not so large nets, then there'll be all kinds of issues.
So when you say approximating functions, so are you, okay, so I guess is this sort of pertaining to the earlier part of the talk when we're—
No, even this part, you know, like the, I mean, it's like the issue raised by the fact that you're never minimizing or optimizing a divergence, but, you know, some kind of a neural net divergence, right? Not JS or anything.
Right.
So, and that's very different. So it's somewhat unclear whether one can just, derive a formula in the space of all functions and then conclude something about what will happen when you implement those functions as neural nets.
So I guess the question is like, how close is Q going to be to P? Is that the question? If I learn this model,
so
yeah.
Yeah.
So absolutely no. So this I would strongly agree with. Like, if the question is like, I'm going to train this generalized energy-based model, is Q going to match P? No, of course not. If P is my distribution over all bedrooms, then no Q of finite capacity and E of finite capacity is going to give me a generative model of all bedrooms. So evidently, I'm going to just find the best function in my class, which is combining my generator and my critic to P, according to this generalized log likelihood. So I'm going to maximize my likelihood of my models under my data. Will I hit P? Of course I won't, and that I don't dispute.
No, but then it would be, I mean, I don't know how to do it either, but it would be very useful if there was some way of understanding, what is lost when one goes from the space of all functions to neural nets, right? And keep track of that.
Absolutely. No, I think that would be very interesting. So what would be, I think, a really essential thing, in which I absolutely haven't done, is to consider, like, for this given class of critic functions, for this given class of generators, what are the smoothness properties of the distribution T that I can capture? So I know that Barnabas Boxer's group has sort of been exploring these issues in the case of generative models where the generative adversarial networks, I should say, where the critic is an integral probability metric, and the generator network has certain properties. For the generalized energy-based models, unfortunately, my critic network is a little bit messier than IPM's. So I don't have yet results that would correspond to the results that Barnabas has managed to derive for IPMs. But I think that's a very essential direction to go in. But absolutely, like, we don't have any guarantees on how well Q and P agree yet. We're just fitting the best model in our class.
Thanks.
Okay, so we have a few more questions. The first is from Jennifer Vu. The question is there difficulty in going between the different modes in Langeland sampling?
Oh, I saw that question on my chat. I was really happy to get it. So this is actually something, unfortunately, I don't have these figures in this paper, but if you, in these slides. But if you have a look at the appendix, what we have, depending on the settings that we use for the HMC, we can actually jump from mode to mode. And this is really cool behavior. And so you can actually see the sampler sort of going and converging to a horse, and then going and converging to like a vehicle, and so on. Basically, whether you want your sampler to get stuck on a mode or to explore from mode to mode depends on how you run your HMC. And I was actually very happy to see it sort of go from mode to mode, because that seemed to be, in a sense, it's a better sampler, even though arguably it might be a worse GAN if you're just looking at the FID scores of all your samples. So yeah, absolutely, using the software that we have, you can get it to explore multiple modes and not just get stuck on a mode. Yeah.
Okay, thank you. And I guess the next question is from Tan Tong Huan. The question is, did you check that your method does not encourage memorization? The discriminator assigns higher scores to real training examples. Using the discriminator in sampling may encourage the generator to generate the training data.
Yep. Yeah, so I think that one has to be quite aware of the risk of memorization. So in a sense, this also relates to this issue of mode collapse. And I think this is where ensuring, for example, that you're using an energy network which has some smoothness enforced becomes essential, because at least this sort of forces a better behaved energy, I think, surface. So again, like not covered in the talk, but in the paper, we use a number of regularization strategies from the GAN literature also on our functions here. So for instance, spectral normalization and so on. And this is essential. So I think what encouraged me to believe that it wasn't memorizing is that you get a sampler that is actually, with the right tuning, drifting from mode to mode. And when it's between modes, the samples that it generates are actually very definitely not in the training data.
Thank you. The next question is from Abhishek Panigrahi. The question is, does the generalized energy-based model suffer from the issue where the distributions P and Q are disjoint?
Right. So we are, in any practical setting, always in the scenario when P and Q are disjoint. So this is where it's sort of essential to define a notion of likelihood that operates in that setting. The likelihood that we use, this generalized log likelihood, which is actually the slide I have up here, does reduce back to Donsker-Varidan in the event that KL is well defined. However, it is always the generalized log likelihood is also well defined when P and Q have disjoint support. And so it's still a meaningful quantity to maximize in this case. So likelihood isn't meaningful because the ratio isn't defined, but you can still fit a model by maximizing generalized likelihood.
Thank you. The next question is from Mark van der Wilk. So the question is, regarding going between different modes, does this mean that the posterior in the latent space is actually not multimodal, even though you're exploring different modes in the observation space? I guess this relates to the previous question that was asked regarding the HMC sample.
So I actually would be very curious to plot the posterior over the latents, and that isn't something that I've done. I would be really surprised if it wasn't multimodal, but what appears to be the case, at least, is that the modes are not very, very separate from each other, in the sense that, like, we can explore multiple parts of the latent distribution. The reason why I'm quite confident that the posterior is multimodal is that for settings, like depending on how we adjust our Langevin, we can get stuck in individual modes. So if you adjust, like if you set your parameters of your sampler accordingly, what it will do, and this is actually what you can see in these figures here, is it will sort of, depending on where we initialize the latents, it'll converge to one mode or another and get stuck there. If we initialize our samplers otherwise, it won't, it'll explore a little bit more. I should also say that we're running this at a higher temperature than the fitted model. I forgot to mention that. So that's also important. If you run it at too low a temperature, then it does get stuck for sure. So yes, it's definitely multimodal.
Thank you. The next question is from Tan again. The question is, can you please explain again how the model goes between the different modes, even if the regions between the modes are low density and have small gradients?
Yep. So here, a combination of running it at a higher temperature and the fact that at that higher temperature, like the path between the modes isn't too improbable. And so the HMC sampler or whatever your sampler is, Mala and so on, will be able to explore it. So yeah, it's sort of down to the settings of your sampler and the temperature that you run your sampler at.
Okay, thank you. And then I guess Mark's question, maybe I'll just leave that to the end perhaps, just because it relates to Sanjeev's question. And then I guess I have another question. So it was obvious to me that when P and Q are disjoint, that it would be still well defined. Can you explain the intuition?
Yeah. So basically, I think the best way to understand, so this is the lower bound that we have on our generalized log likelihood. And here, I think, if you sort of cache this equation here, so minus E, blah, blah, et cetera, so hold that, and then I'm going to just go back a bunch of slides. And now look at this one. So basically, this expression here, if I replace my F with E plus C, it's the same expression. And so you've sort of got this F, which is a function from some class of smooth functions, which is we're going to choose in such a way as to maximize this lower bound. And so even if P and Q are disjoint, I can still learn a smooth function, which is going to make this lower bound as large as possible. So, if P and Q are disjoint, it's sort of going to be large, as you can sort of see on this plot. It's going to be sort of large where there's more red samples and small where there's more blue samples. And so as an importance weighting function, which measures the mismatch between Q and P, this is still informative, even if P and Q have disjoint support.
So I thought there was a Rothan-Nikodym derivative somewhere still in the objective. Was I mistaken? Or
sorry, say again.
I thought there was a Rothan-Nikodym derivative somewhere in the objective, and then that was
right.
Yeah.
Let me go back here. Yes, that's correct. Let me find where that is. Exactly, but of the target QBE with respect to Q. So this is with respect to this Q, which has support on a low-dimensional submanifold in the ambient space.
I see, and Q sub B, okay, so that is...
Yeah, so Q is this, yeah. So Q sub BE is where I take my my original generator Q, and then I modify it with E.
Take the original generator. Ah, okay, I see.
Yeah.
Right.
Yeah.
Oh, sure.
Yeah. So this is all with respect to this measure of load support. So this is all fine. Yeah.
Okay. Cool. Thank you. I think those are all the questions.
Okay. So I think actually that may bring us to the end of the talk. So the sad news is that you will have to invite me a second time to hear the other bits. However, what I will do is go down to the, kernel beer, which is very important. I hope everyone can see the kernel beer. I'm happy to, I guess, take additional questions.
Okay. Let's see. So, Sanjeev and Mark, do you guys want to discuss perhaps, but Mark's points regarding smoothness in the parameter space?
Yeah. Hi, I'm Mark. I thought it would be easier if I just said the question. Hi, Arthur.
Sure.
Maybe I misunderstood Sanjeev's question, but I interpreted it as being that it seems like you make an assumption that the critic is smooth somewhere, But then when you implement the critic, you're implementing it with a real neural network, which is a rough function. And I thought the question was whether that caused any problems. But maybe I've just made up a new question.
So the smoothness is, I mean, so when we say we assume, oops, sorry, too many features. Let me go back. Okay, so when we say we need the network to be smooth, so this is, for example, needed when we want to compute the derivative of our generalized likelihood with respect to the parameters of the generator network. For this, obviously, my energy function has to be smooth in some sense. What we require is that it's like Lipschitz with respect to x, with some global Lipschitz constant, and L smooth with respect to x, which is to say that the gradients have to be Lipschitz as well with respect to x. So, you know, if I'm using values, let's just say that I don't think that's too damaging an assumption.
Great. Well, that certainly answers my interpretation of the question. So thanks very much.
Yeah.
Yeah, I think what I meant was that, you know, L, what is L? You know, maybe it exists, but it's rather vast. And so in practice, the conclusions won't hold that it's actually approximating this.
Right. So L, right. Yeah, if I have a neural net, like L might be, yeah. So that's, in a sense, like to guarantee the gradient, it may be that these assumptions are strong. Yeah. I mean, you know, the expression that we use for the gradient, nonetheless, we have it. But yeah, it may be that if one considers the entire class of networks, that one could get very steep functions in that class. Yeah.
Thank you. The next question is from Jianfen Liu. The question is, when you run Wanzhong at higher temperature, do you reject the samples afterwards?
So basically, we are just sort of expressing, we are running our model at the high temperature, but it's not that we are using the low temperature model to accept and reject. So we just run it at the high temperature.
Okay, thank you. And then I have a question regarding the first part of your talk,
Sure.
regarding, you know, so if you were critics, so you had the result there if your critics are dense, right? In infinity norm, you do get weakened convergence, right? And then you made a comment regarding mode collapse, right? You know, how that can happen is, I guess you said it could be, may not be smooth, and I was wondering if you can elaborate on that and how that relates to the earlier results.
Right. So in a sense, there are sort of two things that work here. So one is whether KL is 0 if and only if P and Q are equal. And for this, my function class needs to be dense in the space of continuous functions on the compact domain. And we also know if this function, if the functions in the critic class are Lipschitz, then we have that KL metrizes weak convergence. That said, you know, what this sort of tells us is that as Q approaches P, my KL is going to drop, which is good. The question that this slide addresses, though, is as Q departs from P, do I punish it sufficiently? Now, if the departure of Q from P has a log ratio that is incredibly non-smooth, then because I've enforced smoothness on my estimate of that log ratio, I will not penalize that as much as I should.
Right, but it will be non-zero still, right?
It will be non-zero. So in a sense, like it is penalizing it, but it's in a sense punishing like extreme mode collapse less than it ought to be doing.
Right. So you're saying this is an optimization issue rather than an issue with the objective?
Yeah, yeah. I mean, this is a sort of, I'm maybe mixing my metaphors here, because like this is just an empirical observation. It's like, you know, what happens if my model collapses its mode? You know, as far as the properties of the divergence class are concerned, this is telling me that if Q and P become close, or if they approach each other, then KL will drop to 0, and it will be 0 only when P and Q agree, as long as my calligraphic H is rich enough.
Great, thank you. Are there any other questions? Okay, if there are no more questions, that concludes today's seminar. Let's thank Arthur again for the for the thought-provoking.
Yep. Thank you for inviting me.